There was supposed to be someone here that was going to come talk about a blood drive. This is the QR codes for 2 blood drives, I guess, in about a month. So if you want those, you can scan them now, or they're also just, I think I uploaded them to Canvas as well. So give some blood if you got it. And now, let's talk about finals real quick. So I made an announcement last night, but last week I put up some final exam info on a Canvas page, but I realized I didn't bump it anywhere. So now I did, but you should also be able to find it just on one of the modules on the Canvas pages that says final exam info. It's right next to all the practice finals that I uploaded. Again, those practice finals, just like your practice quizzes, are not ones that I wrote. They're just from past semesters. I did take influence from them, and I'm aware of their difficulty and content. So I think they are very helpful, but it doesn't mean my final will look exactly like that. But in general, it'll be close-ish. It's not going to be just some alien form. You've seen a bunch of quizzes that I wrote, and I will be writing the final with some TA support and feedback as well. But it is all coming from me, so you know what the type of exams I give. I would say difficulty is probably going to be somewhere, I think I said this, but harder than quiz 2 through 4, but not quite as hard as 1 or as confusing. So that's my goal. If it doesn't work out that way, that's why there's a curve. But I would expect it to be a medium hard, a little bit harder quiz. There's going to be 5-ish questions. I say 4 or 5 just because I think we might be combining the angular and linear momentum stuff into a single problem, which might be a little hint that circular motion could be important. Remember, the ball spinning on a rope, around in a circle. That's a great place, to see an intersection of linear momentum and impulse and stuff like that, as well as angular momentum and moment of inertia and stuff. So won't say too much more about that, but those will probably be one question, maybe a little bit longer, and I would, review circular motion type stuff from both the linear and rotational perspective. Other things that you will probably see on there are things that you have not been quizzed on, mainly capacitors and exponential change. So there's another thing. Exponential change I will ask about, certainly. But I don't want to do a very mathy question about it. What I mean, you will have to do some math, but what I mean is you're not going to have to do a lot of exponential manipulation and stuff and plugging in and using the result of one exponential for another. What I really want you to do is know how they work. So if I want the charge on a capacitor, I want you to know that if it's charging up, it starts at 0 and rises and then slows down until it reaches its maximum asymptotically. And if it's discharging, the charge leaves really quickly and then slows down to a 0. I want you to know that general behavior and be able to identify what is the current in this resistor going to look like over time? What is the voltage across this capacitor? That type of stuff. The math is going to be along the lines of what is the initial value for this? Or maybe I could ask you about here, what is the time constant, right? You'll have an equation for that. So I'm not going to have you conjure stuff up or derive new equations, but plugging into equations and being able to explain what the result means, right? So if I ask you what is a time constant, you should know that. I don't think I'll ask a question so just direct like that, but what is a time constant? What's a half-life? And being able to plug in, maybe go back and forth between those two, which I also will give you the equation for, but it's important to conceptually know what they mean. Anyone can plug in RC to the half-life formula, but being able to tell me what a half-life is very important. So anyway, capacitors and exponential change. I'm not going to ask you anything about exponential change for fluid circuits. That will all be steady state with Bernoulli's equation and stuff. So you will also probably see that. But you have been quizzed on that. Another thing is the stuff we're doing now. So Newton's laws and kinematics. Have not seen a quiz on that. Hopefully it's kind of fresh in your brain. Haven't had a ton of practice with it, but you will see a question on that as well. So those are the new things, or not new, but things you haven't been assessed on yet. It's capacitors and exponential change within that. angular momentum and stuff like that, which will be kind of wrapped in probably with linear momentum and collisions and impulse, like that whole set of stuff, and then Newton's laws and kinematics, which is, Newton's laws aren't that new of a concept. It's kind of, we're not going to have questions that are directly like, what is Newton's second law, or nothing like that, but you should be familiar with all of them because they're really integral in knowing how forces and stuff function. Like third law pairs and stuff like that are very important to be able to identify. And then also just going from there, once I can draw out all the forces and seeing what forces are acting on what things and when, figuring out how that affects their motion. So that's the kinematics part. Force leads to acceleration, which tells us something about our velocity, which tells us something about our position, and drawing graphs for those things. That's another one of the areas where I'm not going to have you do crazy intense math. Like, you're not going to be doing derivatives or integrals or really super complicated stuff, but you will have equations that you should be expected to plug into and know what the answer means, and then also be able to make plots, like sketches of what acceleration looks like over time, what a velocity and position look like. You will only see questions where acceleration is like constant. So you're, gravity or a force push, or at least piecewise, I guess. So piecewise just meaning that like you'll have 0 acceleration here, then 10 meters per second squared, then -8 or something like that. You're not going to have acceleration that's like a function of time or something like that. So constant acceleration, we'll talk about what this means a little bit more as we move through today's class. But yeah, what else? Finals in Geit Hall next Tuesday from 1 to 3 p.m. All this stuff about which room you're in is on Canvas and will be clear if you just arrive there. But please have your student ID with you and make sure you have your symptom survey. Don't want to turn people away because of the symptom survey, so just make sure at some point this week or early next week you make it in for a test or something like that. Any other questions about the final? I'm sure there's some things I missed, but I'll be updating this Canvas post and making announcements as more stuff comes out. Review session stuff should be up by now. Mine are tomorrow and Friday, both in Physics 185. I can't remember the times off the top of my head, but it's like mid-morning, midday. And the first one is going to be, I think, it's posted on Canvas, but I think the first one is more like a lecture style that I'm planning to do. I'll still take lots of questions, and I'm not going to have like slides or anything, but it'll be more of a directed walkthrough of the topics that we went over. And then on Friday, I'll do more of like my normal office hours, which is just fielding questions, going over problems that people want to see, less structured. And then you are welcome to go to those. Any other TAs, review sessions, not just yours, they're not mandatory. So go to whichever ones work best for you. Go to as many as you need. Ask people what types of, or ask the TAs too, like what types of things they plan on doing and what you need the most help with. Any questions about anything from logistics to like tips to preparing, anything like that? All right. So let's get started with today's material then. Newton's laws we went over last time, but just to restate them real quick. Our first law is an object at rest stays at rest, an object in motion stays at motion. It really just means if net force is 0, our velocity is not changing. It doesn't mean we have 0 velocity. I can be moving with a constant velocity, but if that direction of the velocity changes or its magnitude, if I speed up, slow down, or turn, we need some force to do that. If there is some net force, that's where a second law comes into play, then the result of that force is ma, is some acceleration that is related to the mass. So I apply a force to something and its velocity will change, which is what an acceleration is, a change in velocity over a change in time. And the bigger the mass, the less acceleration something going to experience from the same force, which is really just saying bigger objects are harder to move. Right, so these, this is kind of just illustrating how these laws are not something that you need to study and memorize. What's the second one? It's just what does 0 net force mean? What does having a force mean? And then the third one, basically every action has an equal and opposite reaction. This is just if object A applies a force on object B is applying an equal and opposite one on object A. It's very important to note that, or like fall into the trap, it's very easy to, that net force, this does not mean that net force on A or B individually is 0, right? The key here is that this is F on A. This is F on B, right? Net force would only be 0 if all the forces on one thing add up to 0. It wouldn't make sense if I wanted to see what happens to me and this chair, and this chair has been a great companion to me during this class for force examples, but if I push this chair, there's clearly a reaction for both of us. I get some jolt and the chair moves. The net force on either one of us was not 0. There's a force on the chair by me and a force on me by the chair. I don't add those two together to get 0 because they're on different things. If I were to consider the whole system to be me and the chair, then yes, we could say the net force is 0, but that would be an uninteresting way to describe that situation because we're just drawing a box around all the interesting behavior and saying nothing changes outside of that, when really we're interested in how the different components respond. So anyway, third law pairs, really important, but these things are kind of just part of understanding forces. So, like I mentioned before, acceleration is a change in velocity over time, or really the rate of change of velocity over time. The dv dt is how we do it in calculus. It just means an infinitesimal change, or like as small of a change as you can get in velocity over time, and you just add those up to get a measurable change. But really, the d is just a delta. It's some change in velocity, and acceleration is a change. And this is true in all components individually. In our x, y, we're not doing 3 dimensions, but z, they all work independently. And all the Newton's laws can be applied in each direction as well. So if I had an object that I apply a force to in the x direction, then we have, in the x direction, it's going to have some acceleration from F equals ma, from that force that I applied to it, but in the y direction, the force is 0. And so then the first law kind of comes into play there, that there's no net force in the y direction, so it will remain at the velocity that it was at, which was 0 in the y direction. So some counterintuitive things about acceleration, that it can be in any direction, and it doesn't matter you can't, just because something is accelerating, that doesn't tell us any much about what its motion is. Acceleration can mean speeding up, slowing down, or turning. Just any change in this object's motion is an acceleration. And a particle at rest can be accelerating too. That kind of misleading, but it means an object's velocity can momentarily be 0 while it's accelerating, which I'm sure you've seen a little bit so far, and we'll see an example of today. But let's say I'm moving one way, and then I slow down and turn around, right? That whole time, let's say a force was being applied to me to slow me down, stop me, and turn me around. That force was applied the whole time. It was constant, and it caused this change in my motion. And so if the force is constant, my acceleration is constant, right? The acceleration is just force divided by mass, or force is mass times acceleration. But if my acceleration is constant, my velocity was not, clearly, and my velocity was 0 at some point. If I was moving one way, stopped and turned around, I wasn't stopped for any amount of time. My velocity just kind of passed through 0 as it was changing from negative to positive, or positive to negative, but it was 0 while my acceleration was not. So we'll see examples of this. Okay, so there's a couple ways of solving these problems. Again, this is something I just put in here so you can see later in the lecture slides, but when we're doing these problems, it's not new physics. Like I derived F equals ma last lecture, if you remember, from just our momentum, our impulse equation, where delta P is F delta T. I split up delta P and so on and so forth, but they're not like this energy momentum way of thinking of things that we used before is not new physics compared to this force and acceleration way. It's just different ways of framing the problem, and it can be helpful. And it's, you're going to be asked questions that specifically relate to one or the other. But I would think of them as just different models that apply and are helpful in different situations. But the physics is the same. So position, velocity, and acceleration. There's a lot on this slide. I did, again, this is stuff that you mainly might want to review over and you have in your DL and stuff. But I wanted to, I'm not going to do it on the board because I am recording this, but we can walk through what this stuff means. So at the very top, we have A equals dv dt and V equals dy dt. What that means is acceleration is my rate of change of velocity. My rate of change just meaning my delta V over delta t, how fast my velocity is changing and how. And my velocity is how fast my position is changing and how. It's my rate of change of the position. So ignoring all the equations that are up here first, just looking at the top and the charts we have right here, before we even see what this physically means, we can show that these graphs obey the relationship that's described at the top of the page. So let's start with our acceleration. Acceleration here is just some constant negative value in this plot, right? Just some negative, and it doesn't change. This means whatever object this is has a negative change in velocity over a change in time. So as time progresses, we subtract more and more from its velocity. Another way to see that, if acceleration is delta V over delta t, that means each delta t that passes, each second that passes, we apply one more of those delta V's. So looking at it in unit, let's think about gravity. Negative 10 meters per second squared. That's g. That's the acceleration due to gravity. What does 10 meters per second squared mean? Well, it means 10 meters per second, right? There's our delta V is our 10 meters per second, and our delta t is 1 second. That means every second, my velocity is changing by 10 meters per second. So that's the acceleration due to gravity. I drop something, and now it has the acceleration, negative 10 meters per second squared. It starts with a velocity of 0, right? I just drop it. And then after 1 second, it's moving negative 10 meters per second. And then after 2 seconds, I have another delta V of 10 meters per second. Now it's moving negative 20 meters per second. And then after a third second, negative 30, so on and so forth, if that was the only force that was applied to it. But that really, I think, just demonstrates that your acceleration is your delta V over your delta t, and the units, they are meters per second squared, but I would think of it as meters per second. Change of velocity over change in time. So that being said, that this acceleration means that as time passes, I have some delta V that's negative, so subtract off some V, subtract off some more, subtract off some more. So if we take a look then at the velocity plot above it, that's exactly what happens. I have some initial velocity, which doesn't matter right now. We'll see how that comes into play. But what we do want to look at is the rate of change of our velocity, or the slope. How does this velocity change with time? And like we just said from the acceleration, it decreases constantly over time, which is exactly what happens on this plot. All these are, if you can see this top line, these are below the x-axis, so these are all negative, but it's a downward sloping line. As time passes, my velocity decreases and decreases and decreases, and the slope of that is constant because my acceleration is constant. So then let's go one step further. Now we have my velocity, which is my rate of change of position. The units of velocity are meters per second, my delta x over delta p. Every so many seconds, I change my position by so many meters per second. So my velocity is telling me that, well, first of all, it's always negative. So that means over time, I'm always decreasing from my position, or I'm moving backwards, or in this case, down. If we're talking about our y direction, that means I have a negative velocity always. So my y position is always decreasing, going more down. But not only that, now the value of my velocity is changing as well. My velocity is becoming more and more negative. In other words, it's speeding up in the downward y direction. So my rate of change is changing as well. Going from acceleration to velocity was a little easier because my acceleration was constant And so the slope of my velocity, which is just the value of the acceleration, is the slope of the velocity. The same relationship is true for the velocity and the position, but now the value of my velocity is changing. So the slope of my position is changing, which is why we get a curve. The slope starts out at a small value. That's our small negative velocity, right? That means I have some speed and some velocity that's pointing downward. But then over time, due to gravity, it turns out, my velocity the speed increases. Really, my velocity is becoming more negative. And so those jumps in time in my position, my change in position over change in time, or the slope of the position, becomes steeper and steeper. So what this is describing is just, well, dropping an object and having it fall due to the force of gravity. We know intuitively what happens. I drop it, and when I first let go, it's for an instant, but it's not moving. It starts with a velocity of 0, or in this case, it's describing something where the initial velocity is a little bit negative, but we can address that in a sec. But we drop something, the only force is gravity, which is why we get this negative acceleration. So the acceleration is directly as a result of the force, and then it falls down, and what happens to objects as they fall? They speed up, right? And so we would expect my velocity to increase, and my position increases slowly at first, and then quickly at the end, which is described by this increase in slope. The equations that describe these, so these are the ones that I'm expecting you to be able to use and explain, but not like derive, really. So let's start with the velocity one. This one's a little bit easier. So this is, to break this down, this equation says my final velocity is equal to my initial velocity plus my acceleration times time. And this is all the y direction. So keep in mind this is true for the y direction and the x direction completely individually. But since this object is only falling vertically, we only care about the y. So my final velocity is just equal to my initial, whatever I started with, plus the change due to acceleration over time. Right? If acceleration is delta v over delta t, if I multiply it by that time, or my delta t, then I get my change in velocity. And if I add my change in velocity to my initial velocity, I get my final. So that's what this curve for my velocity is describing from this acceleration. Right? I start with my initial velocity here, and then I know my acceleration is some negative number here. So after some time, at t equals 0, this term is 0, right? A times 0 is 0. So my final velocity at time 0 is, well, my initial velocity. Then, after some amount of time, let's say a second, I multiply this negative 10 meters per second by 1 second, and I get minus 10. So that's why this velocity drops some. And then as time grows, my delta t gets bigger and bigger. My acceleration keeps affecting the velocity, and it gets more and more negative, or faster and faster and faster, falling downward. So this equation, it's just plugging in. My acceleration comes from the net force in the y direction. Can divide that by mass to get the acceleration. And then, plug in the amount, how much time has elapsed, and what's my initial velocity. So the initial velocity we need to know. If we were just given this acceleration plot, and we'll see an example of this in a little bit, but if I was just given this plot, that's not quite enough to tell me about the motion of this object. Because I could have an object that I throw down, right? And if I throw it down, maybe like this one, because it starts with some initial negative velocity, then gravity doesn't start acting, it was before, but I was holding it. We're not starting until I let go of it. So gravity's not starting to act until I let go, but it does have some initial downward velocity. Or I could throw an object upward, in which case it has some initial positive velocity. No matter what, while it's in the air, this is what its acceleration chart is going to look like, because it's only affected by gravity once it leaves my hand. Right? I need to know what the initial condition is, how fast it was originally moving, in order to put this onto the velocity chart. In other words, like graphically, this line here, the slope of it, is just a result of gravity. That's going to be the same no matter I drop it, throw it down, throw it up. But where the y-intercept is, or like where this line is placed up and down, that depends on the initial condition. I can move this up a bunch. That would mean that it started with a positive velocity. I could move this up just a little, that I dropped it. This describes something that was moving down already to start with. A very similar thing is true for the next equation, which I'll explain in a sec. But to go from velocity to my position, I need to know where it started, right? So the shape of this curve for my position, my y versus t, is determined just by the velocity, right? What is the slope over time? The slope describes the shape, but did it start at my waist level? Did it start at my eyes? Did it start on the ground? Did it start above my head? All of that is not going to affect the velocity chart, but if we do need it for the position. We need to know where to anchor this curve, right? So that's why in this equation here, in the middle for our y final, we need this y initial, this y naught term. That's just where does it start? That's my y-intercept. And then what else affects my position? Well, we have our velocity piece. So add on to that initial position whatever velocity over time happened, right? So if I started at 5 meters and then I was traveling 1 meter per second for 1 second, then I traveled an additional meter. And so I need to add that 1 meter to my initial position. And then on top of that, then there's this 1/2 at squared piece. We don't need to derive it. It's really integration. It's integrating my velocity, like finding the area under the curve. But really, it's just accounting for, okay, so here's my position. I need to account for the velocity, like what was my initial, how fast was I moving? And then over time, extrapolate that. How much did that cause me to move? And add that to my position. And then to add on to that, if I do have acceleration, my velocity wasn't constant. So I need to factor in the fact that when I was moving like from 0 to 1 second, at that time I was moving at different speed than I was moving from 1 to 2 seconds and 2 to 3. And so that's what this 1/2 at squared piece factors in, is that not only is my position changing because my velocity is non-zero, but if my velocity is changing on top of that, then there's an additional change that needs to be made. So yeah, these come from calculus, but the breaking down of them, I think, is somewhat intuitive in just that for my acceleration, it's very simple. Just F equals ma. To get the velocity, I need to know my initial plus whatever change over time happened, in other words, the acceleration. And then to get my position, I need starting position plus whatever change happened due to my initial velocity plus whatever change happened on top of that due to the change in the velocity or the acceleration. What I mentioned before, that you will not have to do something that doesn't have that has non-constant acceleration, just means that any problem that I give you will have accelerations that are flat lines. There might be a couple of them, or like piecewise, so it might be like flat here, and then flat 0 from this piece to this piece, and then positive over here, but it will just be a series of constant accelerations. I won't have something where the acceleration is changing over time, in which case this gets, like, everything gets more complicated if the acceleration changes over time. But what does it mean for us to have constant acceleration? It just means the force is constant. So for instance, gravity, when something is in free fall, even if I throw it to the left or up or down or whatever, the force on that thing is constant, and so its acceleration is constant. And there's plenty of very interesting scenarios we can describe with pretty complex behavior, despite them having constant acceleration. Okay, questions on this stuff? Hopefully some of this is familiar already from stuff you did in DL. So what was the change here? Yeah. In the x direction, imagine, so that before this was all in the y direction, this was just an object that was traveling downward and being pulled down by gravity. Let's say we had something very similar, except now our initial velocity has an x component, right? So now it's moving down and to the right, but there's no net force. The x direction is, well, pretty boring. Now our acceleration is 0 because there's no net force, so whatever velocity I started with stays the same. We can see that from our velocity equation here, which it's the exact same in the x and the y. My final velocity is just my initial plus my acceleration times time. If my acceleration is 0, then my final and initial velocity are always the same. So that's why my velocity graph here looks like a constant. It is. And then my position is just a line. My position is changing linearly. And we can see that from this x final is x initial, which is our starting point here, which on this graph is 0, plus our v times t, or v initial times t, which we know our v initial is just always, doesn't change, it's the same as our v final. But then this 1/2 t squared term, the thing that makes it a parabola, or like a curve with a changing slope, is gone because our acceleration is 0. So we kind of, in the x direction, this shifted to a simpler system. And the y direction is going to be the exact same as it was. So I guess that's what this slide I kind of skipped over was, if we want to look at the y direction for this object that was initially moving to the right and down, the y direction looks no different to if it was only moving down, right? The x and y directions are completely independent for the purposes of us solving these problems. That's why if I throw an object straight up in the air or throw it to the left and up, as long as they have the same initial upward velocity, that horizontal component does not matter at all when doing this work. We could do it separately and get the simpler work here. And of course, we can always combine them back. If this problem asked for its like final velocity, magnitude, and direction, then I could take my x velocity and my y velocity at the final time and combine them with the Pythagorean theorem, right? Square root of vy squared plus vx squared, and get my magnitude of my velocity. Questions on that? Okay, so why don't we, I guess we can do this real quick. So we'll work on just doing some simple plots of position, velocity, and acceleration. So here we have a box sliding across the ground, no friction. In the y direction, we have gravity pointing downward and normal force pointing up, directly canceling it. So in the y direction, this is a very simple problem, right? It's just our acceleration is 0, our initial velocity is 0, and our y position stays the same. In other words, it stays at ground level. In the x direction, however, there is this force that is pushing this object to the left, or in the negative x direction. And so if we have a constant force in the negative x direction, we have a constant acceleration. And that's going to be negative because, well, it's in the negative x direction. And that just comes from F equals ma. And so if we have some negative acceleration, this ax, here's an example of just like how we might keep track of negatives. Our acceleration in the x direction is negative, and then we put ax in absolute value just to show that, you know, the distinction between an acceleration can be positive or negative, but this is labeling this one as certainly a negative value. Anyway, our acceleration is negative, and so that means the slope of our velocity graph is negative. We need to know the initial velocity in order to go any further. So there's 3 examples here of what could be the velocity over time of this box. And they're all equally right from the information that we've been given so far. Right? We know our velocity over time is just our initial plus at. So the slope of these, that's the at. That's if you have your like y equals mx plus b, or vx equals vx naught plus axt. That's the slope times time. That's just the shape of the curve, the slope of the line. But this vx naught, or my initial velocity, is where we anchor it. What's my initial and where? So we know that the velocity is going to increase in the negative x direction, right? It's going to be accelerated to the left. But if it was initially at rest, or if it was initially moving right or left, then the motion is going to look different. If we're initially at rest, we start at 0 and then decrease from there, which just looks like the box is stopped, and then it starts speeding up in the negative x direction, right? Its velocity becomes more negative, greater magnitude in negative x. If we start moving right, the box is moving right, then initially this acceleration is going to slow it down. right? If our velocity is positive, but our acceleration is negative, then the magnitude of that velocity is going to decrease. Velocity is positive, delta v, or acceleration, is negative, so we're subtracting off from it, which brings the box to a stop, and then it doesn't stop there. It keeps subtracting away. And if we get to 0 and keep subtracting, then it will become negative again. Or not again, but it will become negative, and the box will turn around. So this is one of those examples where the whole time we had a non-zero acceleration. So we have this acceleration is negative, some negative x value. But our velocity was positive at one point, our velocity was 0 at some point, and our velocity was negative at some point. So you cannot tell your velocity just from the acceleration. You need more information. And a negative acceleration can do lots of things. It can slow down, it can stop something, it can speed it up. Finally, if the object was initially moving left, it's not quite as interesting, but it's moving left, we're accelerating it to the left, and so it speeds up and becomes the most negative, the velocity of that one in the x direction. So initial conditions, or these Vx initial, x initial, these are all very important to finding the behavior of a system. Okay, so what does the position of this object look like over time? If our velocity is always negative, or sorry, not always negative, if our velocity is always decreasing, we need to know more about that in order to figure out what direction it's actually traveling. So let's do these individually again. If it's initially at rest, our starting velocity is 0, and so the slope of our position graph starts at 0. All right, so that's why this plot right here shows a 0 initial velocity. Then, over time, my velocity increases in the negative direction, or becomes more and more negative. So the slope of this starts at 0 and becomes more and more negative, or steeper in the negative direction. So this is just this speeding up, and then over time, it covers more ground in the same amount of time. Right? If I take a 1 second chunk early on, it travels some distance here. But if I take a 1 second chunk much later on, then the distance it travels is much greater because it's moving faster. If we take the more complicated example where it's moving right and then the force causes it to slow down and turn around, then our initial velocity is now positive, so our initial slope is positive. Then it slows down, right? We decrease the velocity until it goes to 0. So now our velocity is 0, or our slope is 0, somewhere later on. So this is our position chart, and we know our velocity is 0 when the slope of our position is 0, which occurs at this little bump up here. So the tangent line up here would be flat, or our delta x over delta t would be flat. And then it keeps traveling forward. So this whole time it's in the positive x area. So it's to the right of where it started, right? This is our initial position, and then it gets back to our initial position later on. So this point, at some time t, when this curve crosses the x-axis, and at our start point, these are the same points in space, right? So in order to get from one to the other, it traveled far out, stopped, this is velocity equals 0, and then it turned around and came back. So here, even though my position is positive, when I meant to say position is positive, my velocity is negative, because the slope of this curve is negative here. Positive slope traveling forward, 0 slope stopped instantaneously, right? It doesn't hang out here, but it goes through 0 and then becomes negative, and then it's moving backwards and comes back to its original starting point, and then it just passes through there and keeps speeding up, which is why our curve gets steeper and steeper. The initial moving left case is a little more boring. It's just, starts with some negative slope and then gets even steeper over time because it speeds up in that negative x direction. So yeah, lots of different ways that this one simple example of a box being pushed can look depending on what its initial position and initial velocity are. I guess we didn't really vary initial position here. All the initial positions were 0, right? X is the y-axis, and they all start at 0. But if we wanted to say, what if it starts 2 meters to the left or to the negative x direction of where it started in this one, we would just shift these curves 2 meters down, right? And the shape would be the same. So these initial points, these Vx naught, these x naughts, just shift our initial conditions. All right, so let's do some clicker questions. These are not super quantitative. They're just really making sure we understand how to associate a physical picture with these plots and go back and forth in between these. So, I'm going to walk through this one, and then we'll do the next couple. I'll set you off to do these, and then we'll talk about them. So in this case, we're just in an elevator that's moving upward and then comes to a stop at another floor. So the whole picture that it wants us to plot over time is we're in a stationary elevator for some time, then it starts to move up, and then it goes up to a certain floor and then stops. Right? So we want to see what does our acceleration look like through that whole journey. Well, our initial acceleration, what's the initial picture? It's stationary, right? We're staying in an elevator and it's not moving. So that means our force is 0 and our acceleration is 0. Our net is 0, right? Just because an object at rest stays at rest when the force is 0. It's kind of like maybe overcomplicating it to bring in Newton's laws there, but since the velocity is constant, regardless of whether it's some positive or negative value or 0, there's no acceleration, which all of these obey, right? They all start with 0 acceleration, and that happens to be 0 velocity as well. Okay, then what happens? I press the button, and the elevator goes from being stationary to moving upward. So my delta V is positive, right? I have my initial V is 0, my final V is positive, so my delta V is also positive. And if I have a positive delta V, my delta V over delta T, or my acceleration, is also positive, right? I increase my velocity, positive acceleration. So my acceleration better go up after some time being 0, which all of these also do, right? But then what happens? When I'm in an elevator, does it just keep accelerating over time? Do we just have does it just speed up, speed up, speed up? No, we talked about that last time a little bit, but elevators get up to a certain speed, and then they stay at that speed. They stay at a constant speed or velocity until they get to their destination, and then they slow down again. But we only want acceleration for a certain amount of time to get us from 0 to our desired velocity, and then we can just stay at that constant velocity and travel at that. So A and D do not picture that. Both A and D have a positive acceleration the whole time. D, it's a little more obvious. D has us have some positive acceleration and then stay there until we get to the end, right? So this just means, even though it flattens out, this just means there's still a positive acceleration, right? If acceleration is not 0, that means velocity is increasing. Or if acceleration is positive, that means my velocity is increasing. So even though my acceleration starts to decrease here, this doesn't even mean I'm slowing down. This just means I'm speeding up less, right? But if acceleration is above 0, my velocity is positive, I am speeding up. So case D just demonstrates an elevator speeding up and then coming to a very high constant velocity and then staying there, right? When it comes back to 0 acceleration, that just means now my velocity is constant. But it's huge. This elevator is flying upward and it's not stopping. Similar thing with A. It's shorter, there's not this period of constant acceleration. But even though the acceleration goes up and then down, it's still always positive. So my velocity is still always going up, 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 even though the rate of change might change. It's still increasing. So A and D don't make any sense because that's just an elevator going really fast and not slowing down. So we're down to C and B, which both show an increase in acceleration. So these little bumps bring us from 0 velocity to some positive velocity. They just give us some delta t over a short delta t. And then once they go back to 0, in between those two bumps, that doesn't mean we're stopped. That just means our rate of change, our velocity is not changing. Our acceleration is 0, so my velocity just stays whatever it's at. And if this bump brought us to some positive velocity, we're staying at that positive velocity. So that's our travel time. After that initial time when you like feel the acceleration and you just feel a little heavier for a sec, then the elevator is just moving at a constant velocity. That's the flap piece. Then eventually we must stop. We have to reach our destination, and the elevator has to go from some positive upward velocity back to 0, right? So now our delta t is negative. We're going from some positive value of velocity to 0. And so our acceleration is negative, right? If our delta v is negative, our delta v over delta t is negative. Delta t is always positive. That's just how time works. So if our change in velocity is negative, our acceleration is negative, and b is the only one that demonstrates that. C shows us still, then a bump in velocity from this little acceleration. So now we're moving at a constant velocity, but then we get another bump in velocity, and that speeds us up a little bit more. And then we're back to a constant velocity, but now we're moving even faster than we were before, which is not what happens on an elevator. Instead, we want B, where we're stationary. We get a little jolt from this acceleration, and now we're moving with some constant velocity, and then we get an equal and opposite jolt from that negative acceleration bump that slows us down back to 0. Right? So B is the only one that actually makes sense for an elevator starting and stopping. Let's go through what the velocity looks like for this one. So now it's kind of just an approximation. So this goes into what I said with the accelerations. You won't have like accelerations that are like curvy or changing at all, except for these piecewise things. In that example, you had to pick one because we know they had to increase or decrease at certain points. But those could just be approximated by just like a speeding up, like just a 0, constant, 0, constant, right? We don't need that complex curve there, and you won't for any problem that you have to solve. This type of drawing, where it's just a piecewise bunch of steps for acceleration, is totally fine. Anyway, so this is just recreated the answer here, where we're constant, speeding up, constant, slowing down, back to 0. And so our velocity looks like starting at 0, speeding up, and I guess these are not aligned perfectly because our acceleration, we should have a little bit of time here before we start moving. But anyway, speeding up, constant, slowing down. So even though my acceleration has been positive, 0, and negative, my velocity was always positive, right? It's just the change in my velocity was different, right? It was either increasing, constant, or decreasing. So it's very important. This is a key concept, and like really the thing that I want to ask you on your exams is, can you take a situation, identify what the movement is, and then put it into these graphs? And the more detail, I mean, we'll do some in more detail, and you should get practice in practice problems, and we'll do a little bit more here, but it's just thinking about what times correspond to what type of like acceleration or velocity or whatever, and then from a velocity, can you show me what the acceleration is? Can you get the slope and plot that? From a velocity, can you show me a position? Can you understand that positive velocity means that my position is increasing, or like moving one way or the other? So let's try another question. I'll let you think about this one. I'll give you a couple minutes for this. This one can be kind of tricky. So now we have a ball that's rolling on a ramp. Its initial velocity is to the left. So we just, however it happens, we're starting when it's already moving with a constant velocity to the left to start with. And then you know what happens when the ball is on a ramp. It goes up, turns around, goes back and forth. Right? So what it's asking for is for you to plot the one-dimensional acceleration. And what that means is just its acceleration like along its plane of motion. Don't worry about splitting it up between x and y and stuff like that. Just how fast is it rolling along this track? Or how fast is it accelerating? So I'll give you a couple minutes with this. I'd try to follow a similar set of steps that I did with the last one. This one's kind of tricky. And I realize I don't have the iClicker cloud open today, but just hold the answer up there. I'll give you another 30 seconds or so. And even if that's not enough time to finish, just see what progress you can make in eliminating or deciding what features you're looking for. All right, so let's start working through this together a little bit. We'll do a similar type of thing, kind of process of elimination. So at first, it's moving at a constant velocity. And the net force on it is 0, right? There's gravity down and the normal force from this flat plank up, but it's just rolling to the left at a constant velocity, which we know requires no force or no acceleration. So our initial acceleration needs to be 0. And all of them except E satisfy that, right? E shows an initial acceleration of negative, which means right away we would have a negative delta V over delta T, where our velocity would be increasing in the negative direction. Since the ball is already moving to the left, or in the negative x direction, then this would just mean it would be speeding up right away to the left, which is clearly not going to happen if it's just rolling across a flat ground. So E's gone. Then what happens? It rolls up a ramp. So we could draw out the force diagram, which I'll show on the next slide, but we know that that doesn't, we know what that does. But when something rolls up a ramp, it slows down and turns around and comes back the other way, right? So this ball is going to roll up, slow down, come to a stop, and then come back the other way and speed up as it rolls back down the ramp. So what does that look like in terms of acceleration? Well, its velocity is at some negative value, right? It's moving to the left, and then it comes to 0. So that's a decrease, right? It goes from positive to 0, or sorry, negative to 0, so that's an increase actually. So its speed decreases, but in this case, our velocity along this ramp is positive because we go from negative to 0. Then, once it reaches a stop, it goes from 0 to some positive value, right? It turns around. It goes up, turns around. And 0 to a positive value is also an increase. So that's a positive acceleration the whole time. As soon as it gets onto this upper ramp, whether it's still slowing down, coming to a stop, or turning around and speeding up, that's all a positive delta V over delta T. It depends on what point we're looking at to see what exactly it's doing, whether it's slowing down or speeding up. But no matter what it's doing, the change is in the positive x direction. And so we're looking for a positive acceleration. So A does not satisfy that. B does not satisfy that. C does, and D also does. So A and B show that it was moving at a constant velocity to the left, or 0 acceleration. That's all good. But then both of those show then a negative acceleration, which would mean it goes up the ramp, and then it speeds up, right? We subtract away from this already negative velocity. It gets bigger and bigger in the negative x direction, and we know that that's not what happens. When a ball hits a ramp, it doesn't just speed up and fly off of it. So we're left with C and D. Then what happens? Well, it comes back to the flat ramp. We know no matter what its velocity is, there's no net force or no acceleration when it hits the flat ramp. So its acceleration is back to 0. It's still moving, and now with a velocity that's in the opposite direction that it started with, but that velocity is not changing. So the delta V is 0. So we need to go positive to 0. And only C shows that. In D, we do go down. We drop down from this positive acceleration, but we go right to negative, which means that this ball would be going up, turning around, coming back. So that's the positive acceleration part. But then it shows that immediately after that, it has negative acceleration. So that means immediately after it gets off that ramp, then it starts slowing down again and turns around, which is not what happens. When it reaches this ramp, when it reaches the flat part, it doesn't slow back down. It just remains where it was, assuming there's no friction. So that's why it goes back to 0. And then once we reach the other side, the opposite type thing happens, where now it's traveling in the positive x direction. It goes from positive to 0 as it slows down, rolling up the hill, and then from 0 to negative. So that whole time it was a negative change in velocity. Positive to 0, 0 to negative, that's all negative acceleration, which is why after this constant acceleration period, then it goes back. Then it goes to a negative acceleration. And this cycle will just repeat and repeat, where when it's on the right side, it has a negative acceleration because this wants it to slow down and roll to the left. When it's in the middle, it's constant. And then when it's on the left side, it has a positive acceleration because this ramp wants to push it to the right or slow it down and push it back to the left. Okay, so that's talking through it. Let's see some plots for this. So C is the answer. What do the forces look like at each point? So initially, like we said, net force is 0, has some negative velocity to the left. That's fine, doesn't affect the net force, so we have a 0 acceleration. Once it reaches this ramp, I won't go in detail through the force diagram, but we've seen these before. Gravity and normal force do cancel in the plane of the ramp, but we know gravity has a component that pushes us down the ramp, right? We can go back to force balancing, and if you're not confident with this, I would highly recommend you review it at some point. But, I mean, intuitively, we know that balls roll down ramps. So if you take nothing from this class, that's a great one. But now we know that the net force is going to be down the ramp. And so we have some positive acceleration, the positive direction on the ramp, which at first slows it down when its velocity is up the ramp and the acceleration is opposite that, we're slowing down. And then the velocity switches directions, but the force was the same the whole time. The force and the acceleration were the same the whole time. Gravity doesn't change. The normal force doesn't change. The angle of the ramp does not change. So that force and acceleration are the same, despite the velocity of the object changing. Right? The velocity is just like the result of the acceleration. But that acceleration that caused it to slow down, stop, and speed up in the other direction was constant. And that's why this bar is flat, because gravity doesn't change. Then we reach the flat side again. Velocity is flipped from when we were here last, but it doesn't matter. Our acceleration is 0 because it is flat, net force is 0. And then the opposite happens when it goes on the other ramp, where there's this net force down the ramp. And so we get some negative acceleration. And whether that is slowing down the ball that is rolling up the ramp or speeding the ball up when it's rolling down, it's still the same negative acceleration. Yeah. So now, let's try to plot the velocity for this. So there's two ways we could do it. One, we can kind of step through as a story, the way I just did, and kind of like, we know intuitively what this is supposed to look like, and so we could just take that and plot it. The other thing we could do is take the acceleration chart that we just made and use this to plot the velocity directly from this without going through the word problem again. The one thing we were missing, we do have it, but the one thing this chart does not provide is our initial velocity, right? We need to know where to anchor it, and that's given to us by saying that the initial velocity is to the left. So let's go through this together both ways. First, let's do the story, and then let's do directly from the plot that we already made for the acceleration. So kind of quickly, initial velocity is to the left, so negative, right? And that's constant until we hit the ramp. So we start off with a negative constant velocity. A has that, B has that, C doesn't. C has positive velocity always. So that would just mean a ball that's always moving to the right. That's not the case. D does start with a negative constant velocity, and so does E. We can quickly rule out E as well, though, because E shows always negative velocity. So this is just a ball that at different speeds is always moving to the left, which we also know is not the case, right? So C and E are both gone because we know this object needs positive velocity at some point and negative velocity at others. So let's try to distinguish between A, B, and C. What happens when the ball hits the ramp? Well, we decided, well, forget the acceleration. Right now we're just telling the story. The velocity is negative, and then it goes from negative to 0, and then 0 to some positive value. So which of these do that? A does that, right? We're negative, and then it increases through 0 up to a positive value. B, well, it does do that, but it has this weird blip in it, where at one point it just gets faster for a sec, which that's not the case. So B is gone. There's nothing that would cause this to be moving left and then speed up really quickly before it slows down and turns around again. So B is gone. D also shows that, right? D also works, shows the same thing as A, where it's moving at constant negative velocity, and then it slows down through 0, turns around, and then is moving in the positive x direction. So now we narrowed it down to A and D, and they both actually have pretty similar qualitative behavior, right? They both, after that increase, go back to a constant velocity, which is what we want, right? It is not 0 because it is rolling to the right, but it is positive. So that's this flat piece here. I'll say it's talking in shock. I do have a pretty recent COVID test. But then, after this constant piece, it slows back down again. That's when it hits the ramp on the right, and it turns around. So that's what happens for both of these, where we go from a positive velocity through 0 back to negative. That's it rolling up to the right, and then rolling back, and then back to constant. So both of these do qualitatively work for this scenario. So what's the difference? Well, we can look at the steepness of these two, right? A, the steepness is greater on the left, so for this left ramp earlier on, and then it's more shallow. So the change happens more slowly for the ramp on the right. Whereas for D, the slower change happens on the left, and the faster change happens on the right. So intuitively, we could pick between them because, well, which of these ramps is steeper? Well, the one on the left is steeper, right? If we look here, the ramp that the ball hits first on the left is steeper, and so that's going to cause, we know just from life experience, that the ball is going to stop and turn around quicker on a steep ramp than it will on a very shallow one, which will take longer. So from that, we can decide that A is, in fact, our answer. D would be if this ramp was flipped around, and there was a shallow ramp first on this side, and then a steep one on the other. But this is also cool in that it shows us the kind of the relationship between velocity and acceleration more clearly. Acceleration is the slope of our velocity, right? So the steepness of this is the slope. So since this line is less steep than this one, this means that this has a smaller magnitude of acceleration than this one. And what causes the acceleration? Well, the force. And what causes the force? Well, the incline of the ramp, right? The steeper the ramp, the greater that piece of gravity that's aligned with the, that's parallel to the ramp, and so we get a larger force and a larger acceleration. But like I said, let's relate this to our acceleration plot that we made before. So instead of telling that big story, let's just use this plot here to make one of these graphs. The only thing, like I said, we're missing is the initial condition of what is the starting velocity. We're told that's a negative, so same way we can eliminate C from that because it doesn't have a negative starting velocity. But from there, this plot shows us that the velocity is constant, right, which A, B, and D have, and then the acceleration is positive. So my rate of change of my velocity is positive, which A and D have, right? They go constant, and then the slope is positive, the rate of change. But B doesn't. B has an area of negative slope, right? It decreases, which means that for B, we would need some spike of negative acceleration here, which doesn't exist. Then after that positive acceleration or positive velocity slope, we need a constant velocity, right? Acceleration of 0. Both A and D have that. And then after that, we need a negative acceleration or a velocity with a negative slope, which again, both A and D have that. The thing that we need to distinguish between A and D is what the magnitude of the slope is first at the first ramp and the second ramp. And for that, we need to look at, well, the magnitude of the acceleration that we drew. This graphic on here is very unclear. They look like they are about the same. But in reality, we know that the steeper ramp should produce the larger acceleration. So this constant value here would be higher or have a greater magnitude away from 0 than this one that happens second. And so whatever magnitude this is, that tells us how steep it is, right? So if this is bigger than on the left, then the line on the left should also be steeper in the velocity graph. Questions about this one? So this stuff is super, super important. It gets a little bit messy, especially when numbers come into play, because you have this side of stuff that I'm walking through now, the qualitative, what is my force, what is my acceleration, my velocity, position, stuff like that, which that's one whole can of worms. And then the other piece, which is the equations that I introduced at the beginning, which is given the value for my initial velocity, given the value of my acceleration, what is the position at time t, that stuff. It's just an expression of this. It's how we do it algebraically, but we need to be able to combine those together. So you might have to figure out, I know my graph should look like this, but what is the slope here numerically, which would be my acceleration? What is the acceleration, the slope of my velocity graph? Or at what time, what should I label the time at here? What time does it turn around or something like that, which we will also do some practice, maybe not in class, but certainly in review sessions and in your practice problems. This one maybe we'll go back to. Guess not. All right, so we'll just do this one. I just showed us the answer, so I'll give you a sec to think about it, knowing what the answer is if you saw that. But we have two asteroids colliding, so this is a problem we should be super familiar with. They collide, there's no net force, so they simply exchange forces, right? Newton's third law tells us equal and opposite forces are produced. Force on 1 by 2 is equal and opposite force on 2 by 1. Or in a momentum chart, we would see those equal and opposite delta P's with no net force. Great. But how does this even happen? Why is there any change? Why is there any force or acceleration? Again, because there's a force on 2 by 1 and a force on 1 by 2. We don't combine those together to make a net of 0 because we're looking at these objects individually within our system. So what happens during the collision? I guess we'll just walk through these instead of doing it as a clicker question. Do the two asteroids experience equal and opposite accelerations? Well, that is an attractive answer because we know equal and opposite, that's a good thing. Newton's third law, great. But is Newton's third law equal and opposite accelerations? No, it's equal and opposite forces. So the forces that they exert on each other are equal and opposite. How do we relate acceleration to force? Well, F equals ma, right? And I think I have it written out here if you can see this, but I'll talk through it as well. Force on 2 by 1 is equal to negative force on 1 by 2, or in other words, m2a2, so mass times acceleration for object 2 is equal to negative m1a1, or mass times acceleration for object 1. So if the mass of object 2 is bigger than the mass of object 1, then the acceleration of object 2 needs to be bigger. And I think I wrote it on the board backwards up here. In this case, object 2 is lighter. So I don't know, the way this question is phrased sucks a little bit because the objects are labeled with the numbers that these things are also equal to. But really the root of the issue is that if the forces are equal, then the accelerations cannot be equal because the masses aren't. If the forces are equal, and force is equal to mass times acceleration, if the masses are different, the accelerations have to be different in order for the product of mass and acceleration to be equal for both. So if, MV1 needs to, MA1 needs to equal MA2. So since M1 is twice M2, A1 needs to be half A2, which we can walk through in a sec, but that leads us to our answer, which is C. So that slower asteroid, which again, the phrasing of this is a little complicated, or not complicated, annoying. The slower asteroid, which is the heavier one, which is asteroid 1, experiences a smaller magnitude of acceleration because it has the same force applied to it, but it's heavier. So this is just getting at the root of same magnitude force applied to both objects. The heavier one experiences less acceleration. Bigger objects react less to the same forces because they're heavier. They have more mass, more inertia. B, both have zero acceleration since there is no net force. That's that trap I was talking about before. There is a net force because these two forces are on separate objects. If they were applied to one object, then yes, they would add up to zero, but we wouldn't add them together because they're applied to two separate objects. D is just backwards. If the faster asteroid had a smaller magnitude of acceleration, that would just mean both M and A are smaller. That just wouldn't work out. And we don't need to know anything about whether the collision was elastic or inelastic. Okay, I had it on the board, but I could have just shown it up here the whole time. Force is equal and opposite, so mass times acceleration, the magnitude is equal for both. Bigger M1 means smaller M1. Smaller M2 means bigger A2. So let's look at this in terms of a momentum chart. Like I said at the beginning, this is just a different model that we're talking about today. It's not a complete new physical system, or like complete new set of physics. It's just a different way of looking at things, either our force and acceleration or our momentum, impulse type way of looking at things. Momentum, we have an initial velocity or initial momentum for both, where our bigger object is moving to the right, smaller object is moving to the left. They have some total momentum to the right. There's no net force, so that total momentum is conserved. And then after the collision, well, object 2 is still moving to the right. We need some more information about that. But the key piece is that our delta p's are equal and opposite, right? If our delta p total is 0, which it is because there's no net force, this is just two objects colliding, delta p1 is equal and opposite delta p2. And that's the exact same thing as saying that f on 2 by 1 is equal and opposite f on 1 by 2. Because where does delta p come from? A force applied over a time. So these equal and opposite momenta that are being exchanged in this system are just derived from these equal and opposite forces that are being applied on the two objects over time. So if we want, we could make charts for all of these: acceleration, velocity, and position over time. So assume x equals 0 is the collision location, and the collision lasts 1 second. So initially, the objects are moving toward each other, now with the same velocity, different masses, and then afterwards, well, let's get there piece by piece, but like we just said, equal and opposite forces, and so the bigger object is going to experience a smaller acceleration. So our bigger object here is on the left, and we're plotting, let's look at acceleration first. So both constant velocity to start with. So sorry, I said a lot of stuff there, but let's recenter for a sec. And by let's, I mean let me recenter this for us. Here's our acceleration on the bottom. We have acceleration, then velocity, then position. So let's first look at acceleration for these two asteroids, asteroid 1 and asteroid 2. When they're moving toward each other, they have no acceleration, right? That's constant velocity. We know their velocities are in different directions, but acceleration charts don't take into account velocity, just the slope of the velocity. And then once they collide, they both experience opposite directions of acceleration. They're not equal and opposite, like we just said, because the masses are different, but one of the accelerations is positive and the other one is negative. And because asteroid 1 is heavier, its acceleration is smaller. Same force that's causing these, or equal and opposite force that's causing these, however, since the mass of this one is bigger, the acceleration, or its reaction, is smaller. And this one's lighter, so the magnitude of this acceleration is larger. And then after the collision, they're moving at a constant velocity again, because the thing that causes the acceleration, is only applied while they are colliding. Turn that into a velocity chart. Again, now they're constant velocities because their accelerations were 0 to start with. One's positive, one's negative, and then they collide. These forces get turned into, these accelerations get turned into a change in velocity, or they represent a change in velocity, which is why we have a change in velocity for both of these. The negative acceleration causes a decrease in the velocity because the velocity was positive. And the positive acceleration causes asteroid 2 to first slow down, right? Because it was moving to the left, and then it collided with the other one and turned around. So that force is constant the whole time. The acceleration is constant throughout that whole collision, but the acceleration first causes us to go from a negative velocity to 0, and then from 0 to its final positive velocity. It hits the other one and turns around. And then after the collision, asteroid 1, the heavier one, is stopped. That's information we would just need to get. You couldn't solve that without a little bit more. And asteroid 2 is now moving the opposite direction that it originally was. The position piece, this is always, I guess it can be personal what's harder for you, but for me, I think the position piece is the hardest because it brings in a non-constant slope. Whenever the velocity is changing, so the velocity isn't flat, that's when we get a piece of a parabola, or these curves. But really, you don't have to be super precise with them, but it is important to know, should the slope be increasing or decreasing? So if we look at the position graph on top for asteroid 1, it's moving, its position is getting closer and closer to 0, or it's moving to the right from the negative x area. It's moving from negative x towards 0. And then during the collision, we see it slows down to a stop at x equals 0. So what that means in our position graph is that it has to get from this positive slope to a 0 slope. So our slope has to decrease. So it's a little tricky to say it all out, but our position is always negative, or it goes from negative to 0. That happens while my velocity is always positive, right? Because it's traveling from negative towards 0. That's a positive velocity. But the acceleration is negative, so that's why it's slowing down. We have a positive velocity, but a negative acceleration, so I'm decreasing my velocity. So I would spend some time with this slide, take a look at asteroid 2, which you can see the position plot for that one is a little weird looking, but you should be able to kind of match up, if this is my acceleration and that's my velocity, how does that translate to these charts? Super, super important to be able to figure out what's going on in these plots. And my review sessions are tomorrow and Friday in the physics building. You can find out all that info online. And good luck this week and on Tuesday.
The review is tomorrow at 5?
Which review?
Physics.
There's a lot of different ones. Mine's in the morning. But there's something posted on Canvas, and I'll post it again too, where it shows all the different TA's review sessions, including mine.